Yeah, all good.
Okay, right. So that's the addition law. The multiplication law of probability. Multiplication is recognized by the word and. So if you read, what's the chance of X and Y happening? That's the multiplication law. If the probability of event A is PA, and the probability of event B is PB, then the probability of event A and B happening is given by PA times PB. Similarly, if there are 3 or more events, then the probability of one or the other of them happening is multiply them all together. Yeah. So again, if we said, what's the probability of 2 6s? Being thrown, that would be 1/6 for the chance of getting a 6 on the first throw, times another 6 to get a chance on the second throw. In total, that's 1/36. Yeah. So if it's and, what's the chance of this and that happening? We multiply the probabilities together. Okay. So if we added a third 6 on there, that would be times another 6. 6 times 36 is 216. Yeah. All happy with that?
Yep, all good.
Yeah, just again, just give me just 30 seconds.
Yeah.
Yep.
Okay. Right. I think we got an example problem on the next one. Right. Have a go at that one. Determine the probabilities of selecting at random A, a man, and B, a woman from a crowd containing 20 men and 33 women. Okay. Remember that your check at the end is that both the probabilities should add up to 1. How are we doing? Who's got an answer for me?
Yeah, 0.6 woman, 0.4 man. Is that right?
Yeah, I've got a few more decimal places than that, but
Yeah.
yeah, rounded to one decimal place. That's correct. So you should have, if the probability of a man is P, it equals there's 20 men over 53 in total, which is 0.3774 to 4 decimal places. If P is the probability it will be a man, Q is the probability it won't, and it will be a woman, and that's 33 over 53 equals 0.6226. Yeah, and if you add both of those together, you should get as near as damn at 1, depending on any rounding. All right. Everybody happy with that? Fairly easy stuff so far. All right. So find the expectation of obtaining a 4 upwards with 3 throws of a fair dice. So the expectation of getting a 4 when you throw the dice 3 times.
Yeah, got it all down. Thank you.
All right with that one as well. So the expectation is the number of throws times the probability. So in this case, it's 3 times a sixth, which is 3/6 or a half. Yep.
Yep.
Right. Have a go at this one. Calculate the probabilities of selecting at random the winning horse in a race with 10 horses and the winning horse in both the first and the second race if there are 10 horses in each race. So I'll just run through that. Let's run through that for you. So question part A is the probability of temperature times, because we're and, that's times the probability of vibration. The 20th times the 25th equals 1/500, which is 0.002. The second part says fails due to excessive vibration or excessive humidity. So that's a plus. So PV for vibration, pH for humidity. We add the two fractions together. We get the common denominators the same, 3/50, 0.067. To do part C, will not fail because of both excessive temperature and excessive humidity. We first calculate the chance of temperature and humidity, 20th times a 60th, 0.001, and then the chance, that's the chance it will fail due to both of those conditions. So the chance that it won't fail due to those conditions, which is written like this with a bar across the top, is that you take the probability that it will happen away from 1, because the two probabilities, it will and it won't, must add up to 1. So we come out with a probability of it not happening of 0.999. Okay? Thumbs up, everyone? Yeah, good. So one more example. This is one that looks at this with replacement, without replacement. A batch of 100 capacitors. Let's just make a note of what we read as we go along. So there's, in the sample, there's 100. Contains 73 intolerance. 17 hypertolerance. The remainder, that below, and the remainder, so that's going to be 10 hypertolerance above. Yeah. Determine the probabilities that when randomly selecting a capacitor and then a second capacitor, both are within the required tolerance values when selecting with replacement, and B, the first one drawn is below and the second one drawn is above when the selection is without replacement. So you're drawing 2, and the first part A, when you draw the second one, you're going to draw with a replacement, and then the part B, when you draw the second one, you're not going to replace before you draw again. All right, have a go at that. It's a little bit more tricky. You've got to think carefully about how that one works. For A, what we got? How have we done that? It says both capacitors are within tolerance.
Uh, 73 over 100 times 73 over 100.
Yeah, we're doing the probability of one being good is 73 in 100. and the second one, there's another 73 and 100, which is
5,329 over 10,000, which equals 0.5329.
Yep, correct. And then B, first one drawn is below, second one drawn is above, when the selection is without replacement.
17 over 100
17 over 100
times
below.
10 over 99.
10 is a 10 above over 99 because we haven't replaced the first one. You get.
I thought that was it, but I wasn't sure.
0.017.
Well, that's top line is 170.
Do you have to show it like that first? Because I've just been
Yeah,
always...
I would. Yeah, I
Yeah,
would.
okay.
I think really, then you're showing your work, and then if you have gone wrong, I can see where the misunderstanding is. Yeah.
Okay. Yeah.
And the result of that is 0.0172. Yeah. Okay. So that's with
Yeah.
and without, with replacement, without replacement. All right. Everybody happy with that? Good. Now we're going to move on to something completely different. Binomial series. Binomial expression is one which contains two terms connected by a plus or a minus sign. Examples include p plus q in brackets, a plus x squared, 2x plus y cubed. Expanding this expression, a plus x to the n for integer values of n from 0 to 6 gives the following results. So if we, what they're doing there, if we take the second line, so any a plus x to the power 0, anything to the power 0 is equal to 1. And that's always the case, and you should be remembering that. Yeah. Just let me look, see what's on the next slide, because I might have this in a bit more. No, that's okay. If we expand a plus x to the power of 1, we get a plus x. If we expand a plus x all squared, what we're doing is a plus x times a plus x. And we, everything in, remember what we do, everything in one bracket by everything in the other. So a times a is a squared. Yeah. A times x is ax. This a times this x is another ax. And then x times x is x squared. Yeah. And then we bring the two ax's together in the middle to leave a squared plus 2ax plus x squared. Yeah. Okay, I'll take one more line. If we multiply out a plus x cubed, what we're effectively doing, I'll just do this on a new page. So we're going to multiply out a plus x cubed. What we're doing is a plus x times a plus x times a plus x. Now, we've already done this bit just now. The result of multiplying those two out was a squared plus 2ax plus x squared. We're now going to multiply that by a plus x. So a squared times a is a cubed. a squared times x is a squared x. 2ax times a is plus 2a squared x. 2ax times x is 2ax squared. X squared times a is a squared x, and x squared times x is x cubed. All right. Now we look for like terms. So we got two like terms here that we can bring together. Got two lots of that, and that's it. So we can go equals a cubed plus 2a squared x a minute, we got we've done that right. Anyone see anything wrong there?
Would that be 4a squared x, Mike? Because you've got an a squared x
Yeah.
in the middle.
What in the middle here?
Yeah.
Two.
2a squared
We
x.
got a.
2a squared x.
A cubed is right, isn't it? Because that's this one times this one. And then we've got a squared times x is a squared x. So that's done the a squared on the end here. Then we've got 2ax times a is 2a squared x. And 2a x squared. So those two in the middle can't come together into a 4, can they? Because they're not the same. One's got a squared and the other one's got x squared.
But couldn't the a squared x and the a squared x that you've highlighted come together with the 2a squared x to make 4a squared x?
Yeah, maybe. Ah, no. These last two should be x squared times a. So that's where it's wrong. This is x squared. Because that's this x squared here times a. So that's ax squared plus x cubed. Yeah. So what it becomes is we've got ax squared plus 2ax squared is 3ax a squared. A squared x and 2a squared x is 3a squared x. That's brought those two together. Yeah. And then we've got 3ax squared plus another ax squared is 3ax squared plus x squared. Hopefully that's what's beside that column here. A cubed plus 3ax a squared x plus 3ax squared plus x cubed. The next line starts with a to the 4, 4a cubed plus x, 6a squared, x6, and so on. Okay. What you should note about that, as that triangle's building up, is that the value of a, sorry, the power of a decreases as we go from left to right. So if we take this bottom one, we start off with a to the 6. The next term has got a to the 5. The third term has got a to the 4, and so on. So the power of a is decreasing as we go from left to right until it disappears completely on the right-hand side. The power of x increases as we go from left to right. So we've got new power of x in the first one. We've got x to the 1, we've got x to the 2, x to the 3 as we go from left to right. Okay. The coefficients, that's the numbers in front. This 2 here, this 3, this 6. They're symmetrical about the center line. So we've got 3 on the side there, 3 there, 6 and 2 4s, 2 10s, 2 5s. Can you see there's a symmetry to that triangle as we continue that expansion? Yeah. Now, if we look at just the coefficients in this table over here, what we have is something called Pascal's triangle. All right. And what we've got is we take 2 digits, the 1 and 3, the coefficient below and in the middle of it is those 2 added together. So we got 1 and 3 again there, and the coefficient below it is 4. We've got 2 3s in the middle here, coefficient below it is 6. These 2 coefficients are 10 and 5. The one below is 15. So you can work out the coefficients in the binomial expansion from using Pascal's triangle. All right. That method is suitable perhaps for values of n of around 10. If you go beyond that, that would become a little bit big and unwieldy. But I'm not going to get you to do any problems beyond about the power of 7 or 8. So you should be able to use Pascal's triangle to find your coefficients for the binomial series. Okay. Anyone having difficulty with that?
Not so far.
Okay. So, for example, if we want to expand a plus x to the 7, which just happens to be the next column in that expansion there, right? We can use Pascal's triangle because we can say it's always 1 and 1 on the outside. And then this 6 comes from the 1 and 5 added together there, the 15 from the 5 and 10, the 20 from the 2 10s in the middle, and so on. So that means we know that we can expand a plus x to the 7 is that we add another row. Yeah. So that's going to be a to the 7. 6 and 1 is 7. So it's going to be 7. We've got to take 1 off the index of a. We've got to put an x on. Then we got 15 and 6 gives us 21. Take 1 off the index of a, add 1 to the index of x. 20 and 15 is 35. A to the 4, x to the 3. We got another 20 and 15 on this side, so we've got another 35. A to the 3, x to the 4. We're symmetrical with our coefficients around that plus sign in the middle, because we've got 35 either side of it. We've got another 21 over here, a to the 2, x to the 5. 7 again from the other side, a, x to the 6, and then finally x to 7 on the outside. All right. And this will become a little bit clearer still when we use it to find some probabilities of multiple items. Okay. Anyone got any issues with that? Anyone that couldn't follow those notes and expand out using the Pascal's triangle? Righto. Determine, using Pascal's triangle method, the expansion of 2p minus 3q to the power of 5. So how are we going to start that?
Would be 2p and 3q at the top, won't it?
Hang on. Two p and 3q at the top. How does the Pascal's triangle go?
So we'd start off as with the 2p and 3q at the top, and then it would go 2p and then 2p q.
If we use the previous example, hang on.
Minus 3q anyway, wouldn't it, actually?
Using
Yeah, minus, not plus.
previous example, yeah. Compare 2p minus 3q with I plus x, yeah, because that's what we were expanding before. So what if I in our new example is equal to 2p, yeah, and x is equal to minus 3q, yeah. So using Pascal's triangle method.
Could you quickly go back so I could just take a picture of it?
Yeah.
Cool.
All right. A plus x to the 5 is equal to, from the previous example, a to the 5, yeah, plus 5 a to the 4 x plus 10 a to the 3 x squared plus 10 a squared x to the 3 plus 5 a x to the 4 plus x to the 5. Okay, so that's the basic expansion. Yeah. So therefore we can say that 2p minus 3q to the power of 5 is where we see a in this expansion, we've got to put 2p. Where we see q x in this expansion, we have to write minus 3q. Am I being very clear here or not?
I think if we write it out, it might be a bit easier, like the actual.
So the a to the 5, so we've got to write 2p to the power of 5. That's the first term. Yeah. And then the second term is 5 times 2p to the 4, so that's 5a to the 4, times x, which is minus 3q. Yeah, all follow that? So that's the second term. The third term is going to be 10 times 2p to the 3 times minus 3q to the 2. So that's that term compares with that term. I'll highlight these in different colors, I think. So this term compares to that one. That one is the A5. Yeah. And then we got plus, that's going to be 10 again, times, we got a squared, so that's 2p squared, times x cubed, so that's minus 3q cubed. So that one is that one. And then we got this one here, so that's 5 times a, which is 2p, times minus 3q to the power of 4. Running that colours now. That's that one. That one there. And the last one I'll leave without any colours. That's plus x to the 5. So that's minus 3q to the power of 5. Okay, so you follow where I got that from. I've taken the basic expansion here, a plus x to the 5 expansion. But where I've seen a, I've written 2p. And where I've seen x, I've written minus 3q, because that's the comparison there. Yeah. What we can then do is say that 2p plus minus 3q to the power of 5 is equal to, and we can get rid of some of these terms in here. 2 to the power of 5 is, so we're looking at this one here, this one, 2 to the power of 5 is 36, p to the 5. 5 to the power of 4 plus that comes out as minus 240. P to the 4. Minus 240 in front of the p to the 4. Q. We'll work out. Let me write it out, and then I'll show you where it comes from. Then plus 720. P to the 3. Q to the 2. Plus. That's minus now. Minus 1080, running out of space as well. P squared Q cubed. Bear with.
So 1080 or what? 9080.
That's 1080. I'll write that again. That's minus 1080. And then the last term is plus, oh no, plus 810. P Q to the 4 minus 243 Q to the 5. Right? So this 36 here comes from 2 to the power of 5. If you do that on your calculator, 2 to the power of 5 is 36. Yeah. This 240 is 2 to the power of 4 times 5 times minus 3. I hope. 5 to the 4, sorry, 2 to the 4 times 5 times minus 3. We got to finish in a minute. We'll have to pick this up again next week.
Yeah, I did get that in the end.
That's what it is it? 2 to
Yeah, I
the
got
4.
minus 240, yeah.
2 to the 4 is 16 times 5 times minus 3. So it's just bringing the constants together into one coefficient. Yeah. The 720 will come from 2 to the power of 3 times minus 3 to the power of 2 times 10. The 1080 will be 2 to the power of 2 times minus 3 cubed times 10. Right? Just let me have a look ahead and see what we haven't done. Okay. There's what there is, all there is left is some problems in the notes to have a go at, okay? So we've got to pick up on this probability next week and use this binomial expansion to work out some probabilities of different items with different probabilities happening. So we haven't quite finished this topic yet. We're going to pick it up next week, okay? I realise that that last little bit there was a bit complicated, but don't worry too much about that because we're going to pick that up last week. But do, if you have time, have a go at the remaining problems in the notes that I've sent out, which are those there. Let's just have a look. Batch of 45 lamps, 10 faulty, 1 lamp is drawn at random, probability of faulty and satisfactory, you could do that. Box of fuses all the same shape and size. Determine the probability of selecting a 2 amp fuse, a 5 amp fuse, and a 13 amp, you could do that. And then when testing 1,000 solder joints, some fail, blah, blah, blah. I think you can do that one too. Any more? Yes, use Pascal's triangle for that, for a couple of expansions. So you could have a go at those as well. We'll pick up on them next week. All right. I can't hang on for longer because I've only got 3/4 of an hour to try and do this, hour and a half to try and do this with the other group. So I need to press on. All right. Everybody happy?
Yep.
Yeah,
Can
pretty
be.
happy.
Right? Yeah. Okay. I'll see you next week.
All right, cheers, mate.
Thank you.
Bye. Bye.
Bye.